Okay, so good afternoon, everyone. So what we are going to be working today is retrieving or first talking about satellite imagery available to us, and then retrieving some imagery and working with that. So for today, I just pushed a new script to GitHub. So if you go ahead and download the GitHub repo, you can go ahead and first do that. And then I want to ask you to create a new exercise, a new RStudio project called 14 Satellite. And as you know, always creating those subfolders of code, data, and output, and then also creating that RStudio project. And then finally moving the partial script that I uploaded to GitHub into the code folder of this project here. So right now I have a few more scripts that you don't have, but you want to have your satellite retrieval mean partial right here so we can start working today. I'm going to give you a quick moment here just to go through that since I just uploaded that script. And then once, after a couple minutes, I'm going to assume that you all were able to do it, and then we're going to get started. All right. Was were you all able to do it? Was it enough time? Okay, I think I'll get started. Oh, sorry, did somebody? I saw Tifton unmuting. Is everyone in Tifton ready to get started?
Yes.
Okay, awesome. All right, so let's do this. Okay, so our goal of today is going to be to talk about one satellite um, mission that is very useful in agriculture, that we're going to use it a lot. I mean, we can use it a lot for this specific exercise here, but it is used a lot for agricultural research, especially. First, because it's a very high quality product, and second, because it is free. So it's a really good option for free imagery for fields, and it does have a lot of features that we would need in a satellite imager applied to ag. So specifically, we're gonna be using a satellite mission called Sentinel-2. The Sentinel mission overall is a larger mission from the European Space Agency, where they have many different types of satellites collecting different types of data using different sensors. The subset of the mission that we're going to be using is Sentinel-2. Sentinel-2 is the one that has multispectral imaging device that is very similar to what we were seeing, like just with multispectral imagery in drones, for example. I mean, the sensor itself is of course different because it has a lot of differences related to, being implemented in a satellite, having the atmosphere in between. But still, the type of data we get is going to be very similar to what you would get from a drone multispectral imager. So again, this is Sentinel-2 is the name of the mission that we're going to be working with, and all the Sentinel missions, so not just the Sentinel-2, but the 1, the 3, 4, I think they have all the way up to 6 They're all launched and managed by the European Space Agency, and ESA is the short for that. So talking more specifically about Sentinel-2, it is a constellation of two identical satellites that follow the same orbit. And you may see people saying Sentinel-2A and 2B. That's the name of those specific satellites. So Sentinel-2 overall is the name of the mission specifically for multispectral imager. And then within that mission, there are two satellites, Sentinel-2A and 2B, and those satellites carry the multispectral instruments that are collecting multispectral images for us. Each one of these two Sentinel-2 satellites carry a wide swath, high-resolution multispectral imager with 13 spectral bands, which is very useful for us in agriculture to keep track of vegetation and land. So this is really something that, a lot of times you may get access to satellite imagery, but it may not have all the bands that you need. And so this here just makes sure that we really have a lot of that information that we would need to make sense of vegetation and crops in general. All right, so something, this is not a full-blown remote sensing satellite class, so we're not going to be talking in depth about some of the characteristics that could come into play here, but some of the really important ones I do want to mention. Every time we talk about imagery in agriculture, we need to think about different resolutions of that technology. And so not only resolutions, but also coverage. I want to show you here. So on your script, if you just click on this piece of the code, it should load this image right below that code. This is basically spatial coverage of Sentinel-2. It basically maps all land surfaces on Earth. We can see here that everything in green, which is basically almost all land masses in the world, have a temporal resolution of 5 days, which means that we get a new imagery at least every 5 days. Then we have some parts of the world that have a different color, so some northern latitudes and also some parts here that are land masses in the middle of the ocean. We get less frequent images. And then we have some parts like Antarctica that we get 10 days access from alternated tracks. Basically, for what we're interested, what we're going to be using, we're going to be getting an image theoretically at every 5 days. Which brings us into the temporal resolution. So this is the temporal coverage. So again, all land masses on Earth. Notice that at least Sentinel-2 does not collect data over the ocean. So anytime that the satellite is orbiting the ocean, it's just not collecting data. So it collects data only over land masses. And then bringing us to our temporal resolution or revisit time. For Sentinel-2, that is 5 days theoretically. However, if you check this map below here, so the color gradient you're seeing is the number of tracks. What does that mean? Because we have two satellites, so Sentinel-2A and Sentinel-2B, they do overlap sometimes, right? So the tracks that they cover will overlap. So we see here, for example, that you get the number of tracks you get changes across the world, and which impacts basically um, how many images you can get really within that 5 day time interval. One example here would be in Georgia, where we're going to be using and pulling satellite imagery from South Georgia. In Georgia, we get a new image about every 2 to 3 days instead of 5. And the reason for that is just because we're close enough to the equator where we're getting more overlap between these two satellites and therefore getting images that are more frequent than the 5 days, which is really great. Now, moving on to other characteristics of the sensor, another one that's really important here is spatial resolution, right? So the spatial resolution of Sentinel-2 images are going to range from 10 to 60 meters depending on the band. And when I say 10 to 60 meters, what I mean is a 10 by 10 pixel size, 10 by 10 meters pixel size is the smallest you can get. And it can go all the way up to 60 meters, so becoming coarser depending on which bands we're using. On a drone, you would basically get the same spatial resolution across all bands. That's, or at least that's common, right? If you think of like one single multispectral sensor, that multispectral sensor is going to give you the same spatial resolution across different bands. Here with satellite imagery, we get different spatial resolutions depending on the band. So this is something for us to keep in mind because it's going to be really important to consider that when thinking of which bands you want to use and what is the spatial resolution that is native to them that you're going to have access to. Now, Sentinel-2, as we said already, has 13 bands. That is really, really great, a really great sensor. If you think of it, having these many bands at this, so having 13 bands and some of them at 10 meter spatial resolution with a temporal resolution of 5 day or less, this is really great, especially because it's free. You know, some of the previous alternatives to this, one of them would be Landsat. So Landsat is another satellite. In that case, Landsat is from the US, so it's a United States operated satellite mission. And it has a longer history, it has a lot of data collected with it, and is also free for public use. The problem with Landsat is that we have a coarser pixel size. So with Landsat, we have a 30 by 30 meter pixel size, and we have a 16-day revisit time. That is a longer revisit time, which is bad, and a larger pixel size, which is also bad. So here we see that the reason why I'm teaching you Sentinel-2 is because of the free options is the one that has the most bands at the shortest revisit time and with a pretty good spatial resolution as well. Now, talking about the spectral resolution. So the four resolutions that we think of on remote sensors are spatial, which is spatial resolution is the pixel size. The temporal resolution, which is the revisit time. How frequently does it come over? With so let me just take it one step back. So four are spatial resolution, the smaller the better. That's the pixel size. Temporal resolution, the smaller the better. That's how many days it takes for it to come back to your field again. So more frequent, the better, right? We have this spectral resolution, which is how many bands it has and what is the how many what is the size of nanometers in the spectrum that are being averaged to make up a band. That's also important here when we talk about spectral resolution. And then finally, we have the radiometric resolution, which we're not really talking about here, but it would be really basically understanding how many levels of numbers can you have to represent a given lens surface. And again, I'm going to put a pin on that for now, because that is not one of the key components of this talk. But here we're focusing on spectral resolution, so number of bands and how many nanometers are average for each band, the spatial resolution, and the temporal resolution. When we consider these three resolutions, Sentinel-2 being free is the best option, really. If you have money, you can invest on other imagery from other satellites. You could potentially collect data for, maybe every day at a sub-meter spatial resolution, but then you have to pay. Of the free options, Sentinel-2 is one of the best. All right, so talking about spectral resolution. So I told you already that Sentinel-2 has 13 bands. Of those 13 bands, some of them are at 10 meters, which is the smallest pixel size you're going to get from Sentinel-2. And I want to show you which ones are at 10 meters. So each one of these vertical lines you see here is a band, or at least, sorry, let me rephrase that. Each one of the vertical lines with a label here are a band available at 10-meter spatial resolution. We see that we have 4 bands at 10-meter spatial resolution. Band 2, which would represent the blue region. Band 3, that would represent the green region. And band 4, that represents the red region. That's all within the visible part of the spectrum. And then Sentinel-2 also give us 1 band on the near infrared region at 10 meters. So bands 2, 3, 4, and 8 are all the 4 bands that we have access to at a 10-meter spatial resolution from Sentinel-2. However, I just told you that Sentinel-2 give us 13 bands. So what are the other bands and what are their spatial resolution? If we go to 20-meter spatial resolution, we have 1, 2, 3, 4, 5, 6. 6 more bands available at 20-meter spatial resolution. So the number of the band here is the number that Sentinel uses to represent their bands. So we see here that bands 5, 6, 7, and 8 are all within the near infrared part of the spectrum. And really, band 5 here could be considered red edge because it is at the edge between the red and the near infrared. So at 20-meter spatial resolution, we get 1 band, which is band 5, that is the red edge. We get then 1, 2, 3 other bands on different parts of the infrared spectrum. And then we also get 2 bands out here on the SWIR part of the spectrum, so shortwave infrared. These 2 bands out here are given to us at 20-meter spatial resolution as well. And then finally, we have 3 other bands that are given to us at a 60-meter spatial resolution. So the coarsest resolution that we get from Sentinel-2. Band 1 is here, which would be within the blue part of the spectrum. And then we have band 9, which would be within the near infrared part of the spectrum. And band 10, which is within the shortwave infrared part of the spectrum. So in total, if you were to count, we have 3 bands at 60 meters, we have 6 bands at 20 meters, and we have 4 bands at 10 meters, making up all the 13 bands of Sentinel-2. And again, just to remind you here, we're getting 13 bands, and they are coming at different spatial resolutions, which is not common for drone sensors, for example. A drone sensor would give you all these bands, I mean, not all these bands, right? It wouldn't give you 13 bands, but it would give you 4 to 5 bands, or maybe 3 to 5 bands, all having the same spatial resolution. So this is just for us to be aware of, and be thoughtful of that when you're trying to use these bands for different purposes. Perhaps so let's say something to think about here. If I wanted to calculate red edge, sorry, not calculate red edge. If I wanted to use the red edge band to calculate NDRE, as we saw in the previous class, I would need to use the near infrared band, which is at 10-meter spatial resolution, which is band 8 for Sentinel-2. And I will need to use band 5, which is at 20-meter spatial resolution. So notice how there is a mismatch if I wanted to calculate NDRE. So we would have to consider that when doing so. All right, so here's a quick question for you to help me answer here. If I wanted to calculate, oh, sorry, I just noticed I've been switching the wrong screen. I was switching my other screen here, not the one that you're seeing. But, okay, coming back to the one that you are seeing. If I wanted to calculate a vegetation index at 10-meter spatial resolution, which vegetation index would you recommend? And what bands would you pick? What is the number of the bands you would pick for that? So let me ask somebody the first part of that question. So if you were to calculate a vegetation index with Sentinel-2 data, and we want it to be a 10-meter spatial resolution, first, what vegetation index would you propose that we calculate?
NDVI.
Sorry, can you say that again?
NDVI.
NGVI, you said, Aman? Yes, okay, we could calculate NGVI. Um, so if we were to calculate NGVI, what are the bins that we would need for that? So what is the number of, what I'm trying to say is if you can tell me the name, but then I also want to know the number of the bin in relation to how Sentinel names them.
Band 8 for NIR,
Mhm.
near infrared.
Okay, and which other?
API. So from visible range, we'll get band 5, band 4.
So bins 4 and 8, right? Because that would be our bin 4 is red and bin 8 is near infrared, right? So we would need 4 and 8. Great. So what I want to propose a different one though. So we know that NDVI can have problems because the red band can saturate and become difficult to differentiate, um, very or healthy crop from very healthy crop. So let me ask somebody else. If we were to choose a different vegetation index, but it's still a 10 meter spatial resolution, which index would you use and which bands would you need for that?
You can also use the green and DVI with band 8 and 3.
Yeah, so we could do green and DVI, right? So when I just said that, because the green band brings us back that sensitivity to high biomass and high chlorophyll. So with the green NDVI, we would use band 3 and band 8. So I want you all to take note of that as well. So let's say green NDVI, and then we need bands 3, which is green, and then band 8, which is near infrared. All right. Okay, so something else that you need to be aware of if you have not been using satellite imagery in general is that every satellite imagery provider is going to have different data products that will relate to different levels of processing. When it comes down to Sentinel-2 in specific, it has the following data products, ranging from level 1, including 1A, 1B, 1C, and 2A. Level 0 is the raw compressed image. So it is the, oh, somebody had a question in Tifton?
No question.
No, okay, sorry. I'm gonna go ahead and yeah, perfect, thanks. So level 0 is raw compressed image and it's not available to users. It is the format that the sensor collects the data that is then uploaded to ESA processing computers to be further processed. The level 0 images are then transforming to level 1A, which is basically taking the raw images, so taking level 0 and decompressing them and developing a geometric model. This level 1A, is also not available to users. The next level is level 1B, which takes level 1A image and applies radiometric corrections to it and is also not available to users. So level 0, 1A, and 1B, they exist, they are part of the processing pipeline, but they're not available for us to retrieve. The two products that we can retrieve are level 1C and 2A. Level 1C basically takes level 1B and calculates top of atmosphere reflectance. What is that? That is basically, so whenever you hear the term top of atmosphere reflectance for satellite imagery, it basically means that the image has been radiometric corrected, which comes down to the bands and the positioning of them within the image. It has been geometrically corrected, which means that it is placed correctly in space. And it is reflectance data already calculated, but at the top of atmosphere, which means that it has not been through any processing to remove the effect of the atmosphere. And that some satellites only provide you that. But that is not the level we want to work with. Even though we have access to that, reflectance at the top of atmosphere is not the most useful because it's not applying corrections to control for atmospheric interference, which could be significant. Therefore, the level that we want to use in this case that is available to us is level 2A, which basically takes level 1C, applies corrections for atmospheric interference, and provides you what is called surface reflectance, or SR products, which basically gives you the reflectance of the surface already corrected for all the noise that there is between the surface and the top of the atmosphere. So this is the product we want to use and download. And if you're working with imagery from other providers, you need to be aware that all of them have different products. Their products are going to be probably named differently, but it still is normally like this. The least processed product is raw image, and then they go sequentially applying corrections to it. And normally the last product that they make available is what is called surface reflectance, which again is what we want because it has been radiometric corrected, geometrically corrected. The reflectance values have been already calculated at the surface level. So these four things is what we need to make sure that we're using that data to make sure we have the best data possible for whatever we're using. So there's going to be a part of this exercise that we're actually going to be retrieving this specific product, and you're going to see how we're going to specify that on the code. All right, so normally I have my resources at the end of the script, but for this case here, I do want to provide some resources up front because they're going to be some of them required and others just optional, but important if you want to read more on this. So one of the resources that is required, and I'm assuming you all did this already, because if you have not, then you're not going to be able to complete today, but I asked you to create your account on this website last class. So you went here, you registered, and you got your account. And normally they get back pretty fast. So let me check if did everyone get a notification back saying that your registration was complete and you had access to it?
Yes.
Okay. So I'm assuming that you did that and you got access already. If you did not, then unfortunately you're not going to be able to complete this exercise today. But this is the resource for you to get that account if you still need to. And then I'm leaving you some optional resources. So there is this documentation on getting started with OpenEO R client. So the European Space Agency and the Copernicus mission, which is the overall name of the mission that handles all the Sentinel constellations, they created an API that can be used by different languages, and then they have this specific resource for R. So most of the script that I developed here was based on this documentation. So if you want to be able to do things differently than what I'm doing, or maybe you want to understand better how these functions work, you can take a look at this documentation here that's going to help you understand that. There is an OpenEO R client cookbook, which is an ebook that also provides a lot of great resources that relate to the API. So if you want to, again, get a different type of data from the API, you want to explore that in other ways, there are some really great resources here. And then finally, my last resource is the Sentinel-2 wiki. So I do want to launch this and show you because I think this is they're all important, but this one is especially important because if you ever use Sentinel imagery for a project or for a paper, you do want to be able to explain things and know exactly what are the characteristics of the sensor. So this is just a wiki for Sentinel-2 mission. It has a lot of great explanations. You can just go through here and understand better. Some of those, those figures I was pulling from this wiki, so can really understand better about the sensor characteristics, and a lot of really great information here. I'm not going to go through all of it, but make sure you check it if you want more resources about the satellite mission itself. All right, so now we're about to get started with retrieving imagery for our cotton field. We can retrieve imagery for any field really in the world, right? This is one of the benefits of this imagery source is that it is not applicable just to the US or just to a region of the world or just to Europe, right? It is an European Space Agency product. It applies to anywhere in the world, so that's really useful. In our case, I do want to show you how we would pull this data for our cotton field. So the same field that we've been working in class. So I want us to pull imagery for that field. Now, what we're going to start doing here is, because we have 3 years of ViewMonitor data, right? So we have for 2017, for 2019, and for 2020. I do want to pull imagery for all those years as well, with this very specific goal in mind. So what I have in mind for us is that we're going to pull the satellite imagery data for the same years we have ViewMonitor data, with the goal of creating at some point, not today, but at some point in this class, we're going to create the spatial temporal stability classes using satellite imagery instead of ViewMonitor data. The reason for that, and the reason why I want to show you that, is imagine you're working with a grower and you would like to know their spatial temporal stability for their field. If that grower either does not have yield monitoring data, or not data, but yield monitoring capacity, they don't have the equipment, or maybe they're working with a crop where yield monitoring doesn't even exist, like peanuts, does not exist commercially. Or maybe it's a tree crop that there's no yield monitoring capacity. Well, my question then is, can we at least use satellite imagery to give us an idea of the spatial temporal variability of yield, even if you don't have yield itself? Because there's going to be some correlations between how well a crop grows and how that crop is yielding in the end, and how that is also connected to crop vigor that is then sensed by satellites. So maybe this could be a very useful tool for you to apply to any field, but especially to fields that you don't have yield data. All right, so from this API, from this OpenEO Sentinel API, there are 2 ways we can pull imagery. One is we can pull all imagery available within a range of dates. So we give a starting date, an end date, and we get all images between that. And then we also have the option of still specifying a range of dates, but then instead of downloading all the images, we basically ask for the API to summarize all those images, let's say by the mean, and then give us just that summary image. What I'm trying to say is, imagine that, I don't know, maybe for a field, you're going to have 30 images, which we will do next class. But imagine you have 30 images for the field, and really in the end, you just want to get the mean or the median green NDVI for each pixel over the growing season. That's what we can also ask this API. We can say, well, consider these images in between these 2 dates. And let's say you have 30 images between those 2 dates. But in the end, I just want the average of all of them. And I just want to get one image, which is the average green NDVI per pixel. So again, just repeating that, we have 2 ways of retrieving data. One is to provide a time window and get all images within the time window. The other option is providing a time window, but just getting the average, one image average for the time period. So today we're going to do the second option. On Thursday, we're going to do the first option. All right, so let's get started with the coding part. Well, I guess before I do that, any questions or thoughts about what we just talked about the satellites, about the resolutions, anything in relation to that? All right, I don't hear anything, so I'm gonna keep moving. So today there's gonna be one package that we have not used yet. It's called OpenEO. This is the package that help us to connect to the API from the European Space Agency. So I left you the code for you to install it. As you know, uncomment, install it. After you install this package, you either add the comment again or just delete that first line of code to make sure it's not active in your code, any install.packages functions. And after you install it, make sure that you just run that chunk so we load all the packages we're going to be using today. So we're going to be using OpenEO to get access to that API. Going to use MapView for interactive maps, Tidyverse for ggplot, dplyr, tidyr things, stars because we will be working with raster data. Satellite imagery, at least from the type that we're going to be using, is in raster format, so we're not going to need stars for that. We're going to need SF as well because we're going to have to bring the boundary of this field. In the map view, we already talked about it. So. All right, the first thing here is going to be for us to bring our boundary. So I'm calling that field. If you want to give it the assignment symbol, let's begin by importing that. What is the function we need here? SF, right? Perfect. On the path, as you know, we're going to have to navigate out. So out of code, out of this project, and then we need to go inside 05 digitizing. And then on the output folder, we have our boundary.geojson. That's what we want to bring in here. If we just read that and print it, you're going to see that it is in WGS 84. I do want to have that in UTM. So then we need here st, what function? Transform, right? So we want st transform. The CRS we need here is 6345. If you just run that and you print it, now we have, oh, Delaware. Oh, wait, 6345. I made a mistake. I made a typo. Let's try again. Okay, that looks better. So zone 16 north. Trying to think here. So for today's exercise, this is not going to be as critical. It will be more critical for Thursday when we're going to create some metrics by pixel. So, you know what? I guess I'm not gonna, let me take a step back and just stop here. Because then next on Thursday, I'll show you the next step. I was gonna do a negative buffer on the boundary for a reason, but I guess I'm not gonna do it so we can actually see what's going on. So yeah, we can just stop here without doing the negative buffer. All right, so we have our boundary. It's always great to check, right? To do EDA in a way that we check just to make sure that it is in the right place. We have not made any mistakes. So if we just run this, that's our boundary. It looks good. It is in the right place, so we can keep going. Okay, so now we're basically going to set up our API call. And there's going to be different steps to do that. The first one is we have to establish a connection. So this script especially, let me just give you a heads up as we move through it so you understand what I mean. So we're going to first establish a connection, and then we're going to develop code to retrieve and process imagery that the code we're developing is in R and in our computer. However, once we establish this connection, we are connected to the European Space Agency server, And even though we're coding in R, we're basically sending this code over to them. So they can collect the data we want in the time we want for the field we want, and then calculate the mean all on the cloud, all on their side. It's not happening in our computer. And then they basically just return back to us the final product. So because we need this connection here between us locally and the cloud of ESA, we are going to have to set up a connection. That's what we're starting up here. So if you just run that chunk with the connection, it has some text here. It's basically, for me, shows loading, and then eventually, oops, sorry, I'm running on the wrong screen. Let me run here. It shows that it's running, and then eventually it goes through. And so it says it is connected to that service. So now we establish our connection. However, we don't have access yet because we still need to log in. And this is where having created your account is going to play a role in. So once you run this next chunk, this login chunk, you can look on your console here. It's going to have a message here, and then it says press enter to proceed. If you press enter here on your console, so I'm on the console right now. I'm right here. I'm not in the Quarto file. If I press enter here, it basically launched on a different window. Let me bring that to your vision, to your field of view. It brought in, when I pressed enter on my console, it brought me over here for me to sign in with my credentials. I'm going to use my credentials that I registered. And once you do that, it's going to grant you access to it. So basically it's asking grant access. You need to say yes. And then device login successful. Did it work for the rest of you?
Yes.
Yes.
Okay, perfect. So once you have your device login successful, now you are connected and logged into their service. So now we can start making some queries using our field and also the dates that we want to ask for imagery to be given to us. All right, so if you go back to R, you notice that now it says on your console, it says login successful, and your console is idle again, showing that it has done what it was asked to do and is idling and ready for the next command. All right, so now we need to start a process. And again, I do want to remind you that all the steps we're doing here, we're using R as the programming language, but they're really following the protocol of the API. So it may seem a little bit different from everything that we've done, but it's just a process. So here we're going to start a process, which I left you here, this object P. You just give it the assignment symbol, and there is a function for processes from the OpenEO package. You just specify it that way and just run it. It may take a quick moment here to go through. I can tell that it's working because I see the stop sign available there, and it was also green here on the side. Now we went through. You can also check on your browser. Sorry, not on your browser, on your console. Once a command goes through, it becomes idle again, which is just this greater than symbol. That tells us that that whatever we ran went through, and we can keep coding now. So we made a connection with the API. We logged in on the API so we can use our credentials to pull imagery. And we started a process, which is basically just telling the server that, we're here, we're going to do some coding, and then we're going to make a request. We're going to make a query. So we just started that process that way. Okay, so now on this next chunk, I'm calling this data. This is going to be the part of the process that we specify what is the collection that we want to pull data from, what is the spatial extent, or in other words, what's the field you want to pull imagery from, and then what's the temporal extent, meaning for which dates. Do you want it just for one date? Do you want it for 5 years? We need to specify that here. And then lastly, for what bands we want to pull this. You could pull for all of them, all the bands, all the 13 bands, but I want to propose that we pull for some specific bands so we can use them. So to specify all that, we come here on data, give the assignment symbol. I want to remind you that we started a process above and we assigned that process to an object called P. So now if we bring P here, we use the $sign, and it has many components of it that we can change. As you can see, the one we want to bring here is load collection. So this is the component of that process we want to bring here. So P $sign load collection. A few things here that we're going to change. The first argument is called ID. So ID, in quotation marks, we want to specify which data product we want. If you remember, we want the data product 2A because that's the surface reflectance. It's the most processed product that we can use. So let's start typing Sentinel-2, Sentinel-2 underscore L2A. This is the ID of the product that we want to pull. So we just said, what is the collection? What is the product we want? Now, the next thing we want to specify is the spatial extent. There is an argument for spatial extent. And here we can just give our field, our field boundary, which is in an object called field. So we said what type of product we want, but that product applies to the whole world. Where in the world we want it? Here, our spatial extent is our field. All right, so we established the spatial extent. Now it's important for us to establish the temporal extent. Well, the temporal extent is going to be the window of time for which you want to pull imagery for. Because we were going to give two values, a starting date and an end date, we're going to use a function list. So list like that, open and close parentheses. I'm going to break line just to make it easier for us to read. We're going to give two dates. So again, my goal with this script is for us to pull data for the 2017 year, which is the first year we have field data for our field. So we're going to come here and give the first date. I want to give it in the format year, so 2017 dash. I want to start pulling imagery from May, so 0501. So May 1st is our starting date. You give it a comma. Let's break line again just to make it readable. And then I want to give it an end date. So for end date, I want to give it the end of the growing season. So it's going to be 2017-11 for November and 30 for the end of November. So we're basically asking for images, any available image between May 1st and November 30th. All right, so now come after the parentheses that you open with the list, give a comma, give a return. We're gonna tell it which bands we want. So I want to ask for more than one, and because of that, we're gonna use a list. I do propose that we calculate green NDVI from this field. And so for us to do that, we're gonna need a couple of bands. And so does anyone remember what was the band ID or what was the band number for the bands that we need for green NDVI?
Number 8 and number 3.
3 and 8, right? Thanks, Polly. So here in this list, you open quotation marks. The way that we need to specify is the word B followed by the number 03 for band 3. So B03 to get that band number 3, B08 to get band 8. And then there is also another band, which is not a reflectance band, but it's called SCL. That layer is a surface classification layer that we're going to use that is going to allow us to remove clouds. So one of the processing steps that our L2A product has is that it has an algorithm to classify pixels in different classes. And one of those classes is actually cloud. That is important because if we can use that band that has data for clouds to basically remove out pixels that were classified as clouds and do not allow them to remain in our image. Because sometimes it's really difficult. Like if you just keep all pixels there, it may be difficult for you to really know if a pixel is cloud or not. Sometimes it's obvious, sometimes it's not. So one of the processing steps that they apply here is to classify all the pixels in different classes, and one of those classes is clouds. So we're going to use that layer to help us filter out pixels that were classified as cloud. And the name of that band is uppercase SCL. All right, so we can basically go ahead. If you got all of your parentheses and commas in the right places, it should run all right. And then if you print this object, you're going to see that this is just specifying. So it's taking all the information we provided and then translating that into a format that the API understands, which are just these pairs here of a feature and a value. So you can see that, for example, we gave it the field boundary. It basically translated that to west, east, south, and north in a CRS that is specifically to the bounding box of our field. Then it has a temporal extent and the bands that we want. This is basically what we just determined here. All right, so the next step here is going to be to define some functions to do different steps. And so these, I left you all the code here just so we could, just so we wouldn't have to create these functions because that is not the goal of this class. But I just want to tell you what these functions here are doing. So the first function, we're going to create a mask to remove pixels that are classified as clouds. So I'm naming this function as filter function. It takes a data in a context. The data side is basically whatever the data you give it, or the imagery data. And it is creating, inside of this function, is creating two classes. One is vegetation, which is using our process to get the classes of our data that are equal to class number 4. And number 4 is a class for vegetation. I'm also creating a non-vegetation object that takes our process, takes our data, and selects only the SCL values of 5. And 5 is for non-vegetation. We want to mask everything else other than 4 and 5, including clouds, which is a different number here. So then this function just returns to us in our process, in our data, anything that is vegetation or non-vegetation, but removes everything else. So this is what this function is doing. I'm giving you the whole function already. So make sure that you run this function so we have it available in our environment so we can use it. So now this function has not been applied yet. We just set it up in a way that to do what we want, but we have not applied yet to our process. So if you come here on the next comment, we have this cloud reduce. So basically what we're doing here, let me take a step here and explain to you the term reduce. So in remote sensing, especially satellite remote sensing, you have a lot of data that you can potentially imagine here. You can have data for the whole world, right? The potential is really high as far as how much data you can get. A lot of times we need to reduce that data using one or more approaches. In our case, right now, what I want to do is I want to reduce the data to only give me the bands that we are interested in and not give me the ones I'm not interested in. So then we use this function for a reduced dimension where we give the data we give our reducer function. Our reducer function is what we just created above. So basically, this function is going to be applied on this reduce dimension. And I'm telling that the dimension I am reducing is bands. Because this dimension here could be other things. It could be space and it could be time. We are reducing bands. We're just keeping the bands that we're interested in, not keeping all of them. So if you just go ahead and run this cloud reduce code, cloud reduce, and you print it basically just shows you again. So it has not implemented everything we're doing up until now has not been implemented yet. We're just setting up the code that will eventually be sent to the API and then run on the cloud server. So if you print cloud reduce, you see that basically this is what it did. It basically created the structure of a language that the API understands. So it's just, I mean, there's a lot of stuff going on here. It's kind of difficult to really make a lot of sense just by looking, but it's basically applying the code that we implemented here on the filter function, and we're reducing that to our data and on the bands dimension. So again, we are doing, let me take a quick step back here. We made our connection, we logged in, we started our process, and now we're adding steps to our process, right? So the first step that we added was to specify what was the product type we wanted, what was the spatial and temporal extent, and what were the bands we wanted to keep. Perfect. We loaded a collection on our process. Then we basically are starting to apply reduce functions to our process, which is to give us some type of summarized data. In this case, that summary, that reduce function is being applied to bands to only keep the bands that we're interested in, which are the 4 and 5, which represent vegetation and non-vegetation. All right. The next thing that we're going to do here is apply to our process another reduce function, another reduce dimension function to basically calculate to us green NDVI. Because remember, the satellite imagery is just the bands. It does not have any VIs calculated natively. So we could download the bands and calculate green NDVI on our side, but I propose that we do that here in the code. So, and by doing that here in this code is basically going to be part of the API call, and it's going to be calculated on the cloud. It's not going to come to us. We're not going to get the bands back. We're going to get green NDVI back already. All right, so let's go ahead and apply this spectral reduce. So we call our process P, give the assignment symbol. We're going to call again this function reduce dimension, where the first argument is the data coming in. I want you to notice that the object that we want to put here is the one that we just worked above, which is the cloud reduce. Why here are we using cloud reduce, but on the first reduce, we just use data? The reason for that is because on this first reduce here that we did on the cloud reduce, on this step, we're just removing the cloud pixels. Once they're removed, then we want to calculate green NDVI. So it is a sequential step. You can almost think of a pipe workflow, although we're doing in different chunks just for interpretability. But basically here, our data was equal to the raw data that we're getting. And now we are ready. The output of this was to remove cloud pixels. So now we want to use that moving forward. So here the data becomes cloud reduce, which is again the step that we did just before. Our dimension is going to be again bands, because we're going to apply this reduce to the bands. And now it's going to be a little bit of a different style of programming. Our reducer here, we're going to create a on-the-fly function for this reducer. The way that we do that is we start with the word function, open and close parentheses. This function is going to take a data argument and a context argument. So this is how you want to specify it. And then you open and close curly brackets and break line. In between the curly brackets is what we're going to tell it of what to do for us. So given a data, which is this cloud reduce, for us to ask it to calculate green NDVI, we would basically, I want to create two intermediate steps or two intermediate arguments, sorry, not arguments, but objects. B3 is going to be equal to data brackets and then B03. So remember, this is just basically pulling that 03 band, which is the green band, and assigning that to this internal object called B3. I want to do the same for B8. So B8 equals to data brackets B0808, like that. And then now we're going to basically type here the formula for green NDVI, which is using the B3 and B8 notation, which is B8 minus B3 divided by, make sure you have your parentheses right, B8 plus B3. And then to make sure that this returns to us green NDVI, that is the output of this. We want to wrap this green NDVI formula, we want to wrap that into a function called return. So open and close parentheses before and after when you give return. So basically what this function is doing, let me try to make it more readable for you. So we're giving it our layer that we already removed the clouds, and then we're applying a reducer function to the bands where we're on that function, the function is extracting the green band, extracting the near-infrared band, bringing them together into the green NDVI formula, and then returning that to us. This is what this reduce is basically doing. Now, if you got all of your commas, parentheses, and curly brackets in the right place, if you run this spectral reduce and you print it, oops, print it outside here. It's again just that pair of feature and then value for the way that the API will understand to do what we're asking. So there's a lot of text here, but basically the package OpenEONR provides us functions that are a little bit more R friendly or similar to our syntax. We give it our inputs, and then it translates our inputs to the language that the API call will understand. That's basically what's happening here. Okay, so let's do one more reduce here, and then I'll give you a quick break. The next reducer that we're going to use is the temporal. So here in this case, the goal of this next chunk is to ask for the API to give us the mean over time. So imagine that each pixel, you have a specific green NDVI for that field over multiple images. So imagine you have date 1, date 2, day 3, and a lot of dates, right? Now what we're going to ask is for, on a pixel by pixel level, calculate the mean of that pixel across all those images that you have available and give me just one image that is the mean green NDVI on a pixel level across the whole field. That's what we're going to specify here on this temporal reduce. So here you have the assignment symbol. Again, when we call the P object, that's our process. Remember that the process is, we're building up this process, right? We're applying different functions to this process that then will be submitted to the cloud. So we're gonna ask again for the reduce dimension function. Our data now, well, let me ask this to somebody. Can somebody help me think here? What should be the name of the object to go under data here?
Spectral reduce.
Can you say that again?
Spectral reduce.
Yes, spectral reduce, right? That's right, because now we want to use what we just applied above of calculating gradient DVI and keep that forward, right? And use this layer as our next layer. Thanks, Pauline. So yes, data equals spectral reduce. Give it a comma. Again, on the dimension argument, now is going to change. Now the dimension that we're going to apply the reduce is the temporal dimension. So we give it a T for temporal. Then we're going to call our reducer argument. We're going to call a function that is function. We're going to allow this function to have the arguments x, comma, y. Open and close curly brackets. We just want this function to give us the mean of x. So we basically get the mean of x, and where x is our data, across all the pixels. So if you run this and you print temporal reduce, you're going to see how that was translated to the language that the API will understand, which is not very useful for us to look at. It's just the way that we would do it. And now basically we have all of our processing steps that we want to happen on the cloud side. So the next step is going to be for us to compile these results. So we come here on this chunk, give it the assignment symbol. We're going to call our process object P. And then we're going to call a function for save underscore result. Inside of this function, we give the arguments data. So now data, we want it to be temporal reduce, which was the last thing we did, right? So on this process, we again, let me come back and just repeat that again. So in this process, the first thing we did, so we started the process and then we started adding layers to it. The first one was to load the collection, that we chose what prototype we wanted, what was the field scale, what was the temporal extent, so then starting and end date, and then which bands we wanted. That's the first thing we did in this process. After that, we created a function to apply a reducer function to basically remove cloud pixels. Then we apply that. So we loaded the collection, we filter out cloud pixels. We then created another reduce function to calculate gradient DVI. So we calculated a vegetation index. Then we applied a reducer to get the mean over time. And so then we just got one layer at the end, and we applied that to our process as well. So we basically have 4 steps that we apply to our process. And now we just want to compile all that in a way that we can send it to the server and then ask for a result back. That's what we're doing on this chunk here. Something else we want to change on this chunk is we want to give it what is the format that we want back from it. So it has an argument for format. We're going to ask for a GTIF, a GeoTIFF with G and T uppercase. If you run that, and we can basically print what result looks like. So this is just, again, another way of translating our code to the language that the API understands. Okay, so we're going to do one more chunk and then I'll give you a break. But up until here, all of these steps, we're using R to program, but none of them have been actually implemented on the data. We're just saving these steps like a recipe, but we have not yet applied these steps to the data, which will happen when we send this request to the cloud implements all these steps, and then it sends back just a result, which is going to be our mean across all the dates. The way that we basically submit this request to the cloud server and get a result back from it is by using a function that if you come here on this chunk, the downloading result, we're going to use a function called compute_result. It has an argument for graph, which is basically, this graph is basically where we give the directions we wanted and how we want to download it, which is what we just compiled on this result object. So graph is going to be equals to result. And then we're going to have here an output file argument as well. So output file, this is where we're going to give a path and also a file name and extension. So we're going to save this on the output folder. So I want to give a // go to output. The name I want to give this is 2017_mean_GNDVI dot, and then we give the extension, which is GTIF, just one F. So a GTIF with just one F. This is basically us compiling all the steps we want to apply, which happen on the result object, where we also gave what is the format we want back from it. And then we compute the results by sending this request to the cloud and then getting back an object that's going to be saved on this path under this file name and extension. If you go ahead and you run this compute results, I actually got an error. Valid password parameters dimension in process reduced dimension is invalid. Let me see here. What did I miss?
Can it be in spectral reduced? Because I also get an error in that part with both.
Yeah, I wonder, I mean, I think I probably made a mistake somewhere in, okay, I think no, I don't know. Let me just check my code here. I'm guessing I probably did something wrong, and I'm not sure where that was. I mean, we could
Maybe the spectral reduce, the chunk for spectral reduce as an error. Yes, that one.
Yeah, let me see. Let me take a look at what I have here. Oh, yes. Okay, I know what yeah. There's a step here. Okay, so if you return to the cloud masking chunk or part of the code, there was one more line of code we need to implement here. So when you come after the mask the bins data, I want to call this object cloud reduced with a D at the end, meaning that we applied the reduce to it. That's what we're missing. So if you give here the assignment symbol, we're gonna call our process object, so the P object, $. We're gonna call a function called mask, where we give our data and our reduce function. So cloud reduce, or reduce object where we're applying the function. So with that, if you run your cloud reduce as we had before already, make sure you run your cloud reduced with a D at the end to apply this, to use the mask function to apply our cloud reduce instructions to the data. So it does actually implement that mask. I mean, we can print it, but it's just the instructions needed here. And then make sure that on your spectral reducer, your data is equal to cloud reduced with the D, which is the one that then already received that mask being implemented. I think that's the step we're missing here. So if you again, on the spectral reduce, part of the code, you're gonna have to make sure that this data object is the cloud reduced with a D at the end. And then you,
Yeah, for us in Tifton, it still doesn't work, that chunk. The spectral reduced chunk.
so,
The error parameter reducer, subgraph parameter X.
okay, so let me try on my side here to see if it's something that is happening with me as well. Yeah, so the thing is, I think now is gonna work, at least on my side. The thing to keep in mind is, let's see, let me check if it goes through on my side. So this loading is just telling me that it was submitted to the cloud server. Yeah, so it worked on my side, so it should work as well on yours. So let's just revisit the change I made and make sure that you all made that change as well. So what we just did here was, so we have a cloud reduce without a D at the end that we already did before. Now what I missed in the code was this cloud reduced with a D in the end step where we do a P $mask. We apply that to our data, and then a function, and then we call this object cloud reduce here. Once you create those instructions that are now assigned to cloud reduced, you want to make sure that on this spectral reduce, you have your cloud reduced with the D at the end as your data. And you need to make sure then that you rerun the spectral reduce, rerun the temporal reduce. So we're not changing the temporal reduce, we just have to rerun it so that those changes are connected, rerun the result, and then finally rerun the compute results. Did it work on your side?
Yes. Yes.
Okay, Benedetta, were you able to do that?
Like I have an output that I'm not able to open, but it still gives me the error in this chunk.
On the compute results?
No, on the spectral reduce, it still gives me an error, even with all those changes, but going through in the end, I have an output, even though I'm not able to open it.
I had an error when printing spectral reduce on this chunk.
I also have that error.
Okay, well, let's do this. Let's try to do the next step, which is to actually check the data that we got. And then if it still works for you as far as getting the data that we were able to retrieve the data, then that's the main part. But if for some reason there's a difference that is not allowing you to even get the data, then we're gonna have to troubleshoot a little bit more deeply. Okay, so we are at 3:40. I think we passed the time of me giving you a break. So let me go ahead and give you a break so you get a 5-minute break. And then once we come back, we're going to basically import this data that we just downloaded. So on my side, if I go to my output folder, I have this 2017 mean-grained DVI.gtiff right there. So we're gonna bring this back, and this came from the cloud, right? It did automatically without us having to do that manually, but it came from the cloud, and now the next step is gonna be to import this into R and just check it out. So let me give you a 5-minute break, and then when we come back, we'll take a look at this layer, and if there's something that is still happening on your side, then we'll troubleshoot that. All right, so let's continue here, and let's see if, in spite of the error that you're all getting, if we are still going to be able to check this. I guess, well, before we go ahead, so Benedetta, you were saying that you were having the issue. So when you go on your output folder, do you see this object or do you not see it?
We all have the error, but in the end, when we try to, it does come in the output folder, and when we try to print it on R, it works. So
Okay, great. Perfect. Yeah, I'm not sure because I'm not getting the error, so that is intriguing, especially if we all have the same code. But as long as we're getting the layer and it works, then that's the most important thing. Okay, so maybe you have already done this on your side if you checked in R, but I want to bring in now this green DVI layer for us to further explore. We're going to use the function read stars because it is a raster file. We're going to navigate there. So // to get outside of the output folder or get outside the code folder and then go inside the output folder and bring the 2017 mean gndvi.gtiff. If you run that and you print it, it is a TIFF file with a raster or a raster object from a TIFF file. We see it has one layer that is naming like this. It's the name of the column, if you think about it, or the name of the data associated with this raster is the same name of the file type, which is well, I want to change that. Also, the CRS and something that we're gonna see especially on the next class exercise, but the CRS seems to be changing when we get the data from the cloud. So one of the things I want to do here is, so if we come back to the code, let's add a pipe. I do want to, I guess, transform again to the CRS we've been using. So let's use st transform with the CRS equals to 6345. That's the CRS that we've been using for this field for UTM. And then I want to do a couple more steps here on the process on the wrangling side. So the first one is I want to rename this column to something that makes more sense instead of the name of the file. So if you come here, let's use the function rename. And I basically want to rename this to gndvi. And I don't know if you remember, but when we're renaming something, we can either give the new name equals to old name or equals to position, right? So it's easier to just say position 1 here because this is the first position than it is to type it out. Let's just say green DVI equals to 1. If you run that and you print it, now on the first panel here, we see the GNDVI name instead. Yeah, so I think we can go to the next chunk now. So the next chunk, I basically just want to take a look at the map view of this. So I need to create an interactive map. Let's create the function map view and the object gndvi_mean. If we do that, this is what we see. So we do get as we asked, right, the green DVI average for the whole field over the 2017 growing season. So again, if you think of it, each one of these pixels has a value, and that value for that pixel is the average green DVI of all available dates for that pixel. This is basically what this layer here is doing for us. Something else we could potentially do here as well is to crop this layer here to only contain our field and not have because remember, with rasters, it's gonna give us the bounding box and all the pixels pixel values inside the bounding box. But let's go ahead and crop this to just the field so we ignore the rest. If you come back to the chunk above, we just need to add an ST crop and then field, and this should work. And now if you go ahead and run your map view again, we should only have the values found within our field. So as we already saw this on the yield monitor data, if you remember, but we have, those eroded sides of the field have a lower gradient DVI mean across the season. So that is something we already expected. If you recall, I don't remember if it was in 2017 specifically, but there was a streak of lower yields, like in this part of the field here as well on the top, that is also coming through as the mean GNDVI, right? And perhaps, again, this is how we're planning to understand if we can use satellite imagery to understand yield variability in this field. If we consider that, it looks like there's a good correlation here between where we would expect to have lower yields, having lower mean growing season gradient DVI. So that's what we're counting on, and we'll be implementing in a future exercise. All right, so the last chunk I want to do here is just to make a static plot. So we're going to use ggplot for that. And then, we're going to call a geom stars, since this is a stars object. Data equals GNDVI underscore mean. If we just run that, that's what we see is the same data as above, just not interactive. And let's just go ahead and change the scale to scale fill varieties C for continuous. So we have that varieties look to our map. So same data, just now as a static map. So did it work for everyone to do this? We're able to import it, process, and visualize the data?
Doctor, I got it's showing me an error, like server error, and when I'm downloading my results.
Is that Mohit?
Yes, Dr. Bhaskar, Mohit.
Great. So Mohit, well, let me ask this. It seems like everyone else was able to do it. So I guess what I'm going to ask is, was someone else besides Mohit not able to do it? Okay, so in that case, Mohit, I would ask for you to post a GitHub issue with the code, with a snapshot of your code and the error. And then Neva is going to take a look at that and see if she can troubleshoot for you. And if not, then Neva will loop me in and then I'll try to help you as well.
Sure, Dr. Bhaskar.
All right, thank you. Okay, so this wraps up this first part of this exercise of using satellite imagery, where today we basically learn about Sentinel-2, some of its characteristics, some of its properties as well. What can you expect as far as what type of data, how frequent, what spatial resolution we get, what bands we get access to, and the resolution of different band groups. Then we basically created a lot of functions here to interact with their API through R. As we saw today, although we were using R language, it was using a little bit of a different syntax than what we've been used to. And that is just because that is the syntax that the OpenEO package accepts, that then is able to translate into the language that the API actually understands. So that's why, like, there were some things there that maybe seemed a little bit different than what you're used to in R, but that is just what's going on there. Also, just a reminder, I did leave you a lot of resources as part of this script. I would highly because so I developed this entire script by using those resources. And so if you want to do something different, if you want to understand what are the options of different functions and arguments that we did use today, I would encourage you to look into that API because that's going to give, or not API, but into those resources of the API so you will just have a better understanding. Of course, in class, I'm already giving you a script that is ready and that it works. But if you want to make changes, you can always explore those resources on your side and learn how to do something else that you may be interested in. And then after that, we retrieved the mean of the growing season for green and DVI for one field and 1 year. That's our summary here. Next class, my goal is going to be to teach you how to pull not just the mean of the field, but all the images that were actually used to create this mean. So we're going to basically be getting a lot of geotiffs from the cloud server in next class, and then make a lot of maps from those different images and so on. All right, that's all I had for you all. I do want to open an issue for attendance on GitHub. So let me do that first. April 8. So I just opened the issue. So make sure you claim your attendance. And if anyone has any questions, claim your attendance and then you're good to go. But if you have any questions, I'm going to stick around for a couple minutes to help anyone that may have questions. So,
I have a question about the last time, not the last time, the one before, we had a problem with the function elide. It didn't work for us. And Polly had found a solution, but in the end, it doesn't work. And I was wondering if there was another possibility to overcome that problem.
Okay, so I have not looked for a solution for that because I thought that the solution that Polly found was working, but since it's not working, I guess what I would say is for that exercise, you can basically just ignore that elide function. Of course, so it is an important step, but I don't want you to get stuck on that without having a solution.
Okay.
And in that field specifically, the tilting of the field is just a little bit. It's not like very drastic as it could be in other fields. So for that field and that exercise, just to make sure you can complete the coding exercise to the end, I was just gonna say to comment off the elide part of the code and just keep running and it should work. Now that is not a solution in the long term if you have fields that really the direction of the row pattern is really off an east-west direction or like a straight east-west direction. In that case, I would either look for another solution in R, which I don't have from the top of my head because I didn't have that problem. Another solution would also that may be easier is not as reproducible, but it's probably easier would be to bring that into a GIS, like a point and click GIS, like a QGIS or ArcGIS. And there you have tools that you can edit the layer and easily tilt in one direction or the other. So as a longer term solution, I think that's what I would recommend doing.
Okay. All right. Thank you.
All right. Thanks.
After that.